Hey guys, in this video we'll be focusing on Boolean algebra. So first, let's us discuss what an axiom is. So basically, an axiom is a statement that a system accepts as true without needing proof. It is like the foundation stone of logic or mathematics. Like, for example, you have a plus b equals b plus a. I mean, what is there to prove here? This is basically true without proving anything. It is like the foundation of logic. So that is an axiom. So I want you to also know something, that the arithmetic operations of subtraction and division does not exist in Boolean algebra, and I'm going to show you how. So we have a plus b equals b plus c. We know that b is equal here. In normal mathematics, we know that from this equation, a must necessarily equals to c. But in Boolean algebra, it is kind of different. It is not a must for a to be equals to c for this to be true. Let me show you something. So a is equals to 1, b is equals to 1, and c is equals to 0. So importing this into this equation, 1 plus 1 equals 1 plus 0. And you know, in Boolean algebra, 1 plus 1 is 1, because true plus true is true, and true plus false is also true, since one of the inputs is true. So you say that it does not necessarily need a to equate to c for this equation to be true. So now you know that it is kind of different. It is not necessarily the same thing. So now the basic rules of Boolean algebra, axioms again. So we start from the axioms of and. For one, the first one is 0 and x is equals to 0. Why is 0 and x equals to 0? I don't know. This is why we call it an axiom. It does not need proof to be true. The second one is 1 and x is equals to x. The third one is x and x is equals to x. The fourth one is x bar and x is equals to 0. Now, this x and x, we might be asked, it is from the idempotent law. Yeah, idempotent law. Now, the fifth one is x and y is equals to y plus x. Why? I don't know how. It is an axiom. This is the axiom of and. Now we will move to the axiom of or. Okay, let's do it here. Or. First one here is 0 plus x is equals to x. Second one is 1 plus x is equals to 1. Third one is x plus x is equals to x. Fourth one is x bar plus x is equals to 1. The fifth one is x plus yz is equals to x plus y and x plus z. So this is the fifth one, and this one is the distributive law. Distributive law. Now there is also this one, x plus xy, x plus xy is equals to x or and x into x plus y is equals to x. This one is absorption. We also have x plus y plus z in brackets is equals to x plus y plus z. The order of subtotal does not matter. This one is associative law. Associative law. Now there is the double bar, just in case you see it. 1, 2 is equals to x. So this is all of them for now. So we will now see some of the province. Let's go to the first one. X plus x and y is equals to x. So x plus x and y, and this is like multiplication, is equals to x. From the basic rules here, so you consider 1 plus x is equals to 1. So if we factorize x out of it to be meaning 1 plus y, right? And we know that 1 plus x is equals to 1. So 1 plus y is equals to 1. That will be x into 1. Like, because they only say that because this is y and this is x, they are just using letter here. So even though it's 1 plus z is equals to 1, if there's 1 plus p is equals to 1, if there's 1 plus m is equals to 1. So 1 plus y is equals to 1, and that's how we have x. That's why x plus x and y is equals to x. Second one, x into x plus y is equals to x. So very simple. We expand. We take, sorry, I've not been mentioning this. We take the left hand side. It is the left hand side we're proving to get the right hand side. So we take the left hand side. So x into x plus y will now be equal to expand x plus x plus x plus y. Now we know from the law, where is it? X times x is equal to x. We know from the idempotence law. So this is x plus xy. Now you can see the same thing here. Factorize x out. That'll be x into 1 plus y will now be equal to x into 1, which will now be equals to x, which is why x into x plus y is equals to x. Third one, x plus y, all brackets, x plus z equals to expand x times x plus x times z plus x, y times x, that's xy, plus y times z. Now remember, x times x, it is x from the third axiom. So x times z is x plus xz plus xy plus yz. Now we can factorize our x from this place. That will be x into 1 plus z plus xy plus yz, because this is 1, x1 plus xy plus yz, then equals to x plus xy plus yz. Now we can factorize our x, bring x out, x1 plus y plus yz. Knowing this is 1 equals to x1 plus yz equals to x plus yz. So we have proved it. Now let's find another question. So this is x plus x bar y equals to x plus y. So remember that 1 is equals to 1 plus y. 1 is equals to 1 plus y. So we bring our x 1 plus y into this place, and we multiply x times 1 will give us x times y will give us xy. Then we write it. Then you can see here our y is common, so we can factorize our y out. Down, I mean x plus x bar. Now remember, x plus x bar is 1. Down, I give us x plus y. Now you can see why this is equals to this. Let us do another question. This one is xy plus xz plus yz is equals to xy plus xz. So from the left hand side, xy plus xz plus yz. Sorry, there's a bar here. The question is not correct. So we know that 1 is equals to x plus x1 from the last question. So we can put it at the back of this yz. That will be xy plus x bar z plus yz x plus y x plus x bar. Now you are probably thinking, why are we putting it in this yz? Why are we not putting it here? Why are we not putting it here? If you notice, you can see this one is xy, this one is xz. So the x is common here. We need this one to come and like multiply, so we can factorize like xy out and xz out. So we will now choose yz, which is y and z. That's why we're putting it here. We're not putting it here. We're not putting it here. So it is yz that will now put it. That's why we're putting the x plus x bar there. So let's continue. Xy plus x bar z plus xyz plus x bar yz. So this is what we need, so we can factorize it out. So let's us rearrange. Xy plus xyz plus x bar z plus x bar yz. So we factorize xy out. Xy into 1 plus z. Now you are seeing what I'm saying. Into 1 plus z. If you put it here, it's not. If you put it here, it's not. It is the yz we have to put it. Plus x bar z into 1 plus y. So now be xy 1 plus x bar z 1. So now be xy plus x bar z. Now you can see why this is equals to this. Now I want us to try one last example. Just manage this space. One last example. So we have x plus y into x bar plus z will give us xz plus x bar y. Now from the left hand side, we expand. X times x bar plus xz plus x bar y plus yz. Now we do the same thing here. But first and first, we see something. X times x bar. On the rule, you notice that x times y is 0. X times y is 0. So this one will be equals to 0 plus xz plus x bar y plus yz. And guess what? We do it again. We have our xz and our x bar y. So we have the x, y, y. We do it again. It is in the y. Z, we add our 1 is equals to x plus x bar. So now we have the xz plus x bar y plus yz into x plus x bar. We expand. xz plus x bar y plus xyz plus x bar yz. We rearrange xz plus xyz, this one, then this one plus x bar y, then this one plus x bar yz, then factorize it out. Xz to 1, what's the meaning? Y plus carry this one out, x bar y into 1, what's the meaning? Z plus z. And I told you 1 plus any letter is 1. So okay, let's continue from this place. Gonna be xz into 1 plus x bar y into 1. Final answer xz plus x bar y. Now you can see why this is equals to this. So this is pretty everything for the axiom parts. Now we'll be moving on to so before we move on to the numbering system, let us finish the theorem. So we have our x, y, z, then x plus y plus z, then x plus y plus z all bar, then x bar, y bar, z bar, then x bar and y bar and z bar. So 0 0 0 0 0 1 0 1 0. It is this is like in the number system. So we start from 1 2 4. So this is our 1, this is our 2, this is our 4. So this is 0 0 0, this is 0, this is 0 0 1, this is 1, this is 0 1 0. So it's 0 1 0, which is 2. So the next one will be 0 1 1, which is 3. That will be 0 1 1. The next one will be 4, which will be 1 0 0. So it's like that, 1 0 0. So the next one will be 5, which will be 1 0 1, which is 4 plus 1, that is 5. This one will be 6, 1 1 0. That will be 4 plus 2, 6. Next one will be 7, 3 1 1 1, 4 plus 2 plus 7 plus 1, which is 7. So that's how we got this. 4 5 6, oh my god, bro. 7 6 5 4 3 2 1 0. Okay, so x plus y plus z 0. As long as there is one, as long as one of the inputs is true, they will all be true. So this is 1 1 1 1 1 1. This is the inverse of this one. That's why that time he's saying that it is x bar bar is equals to x, because this is the inverse of the inverse, which is x. So this is the inverse of this one, that is just 1. So 0 is 1, 1 is 0, 0 0 0 0 0 0. So this is separate form. So x here, it will be 1 here, y here, it will be 1 here, z here, it will be 1 here. X here is what? 0 1 here, y is what? 0 1 here, z here is what? 1 0 here. So this is just the inverse of the values here. So yeah, x here is what here? Still 0. So 1 0 0, yeah, 0 1 1, yeah, sorry, it's not matching. 0 1 0 0 0 1 and 0 0 0. Then this is for the multiplication. Of course, 1 times 1 times 1 is 1. There's 0, there's 0, there's 0, there's 0, there's 0, there's 0, there's 0. So you notice something, that x plus y plus z all bar is equals to x bar times y bar Right. Z bar, because this is 1 0 0 0 0 0 0 0, and this is 1 0 0 0 0 0 0 0. So this is all for the axioms part. So now let us now go back